Usual computer systems use hard disk drive as primary form of storage. Data storage in these disks is getting faster and reliable with every advancement in technology. However, there is always a risk of data loss due to disk failure. Having redundancy in data storage is an important requirement to avoid any disastrous consequences. To add on to this, as most software applications have to deal with large data files, processing or handling of these files can be slower if these are not stored appropriately and effectively. This will further impact performance of a system. In current video, we will talk about RAID and its usage to achieve reliability and performance in data storage. We will also see how it is used to provide data redundancy to protect data from hard disk failures. RAID stands for Redundant Array of Independent Disk. It is an arrangement of several hard disks acting as a single logical drive for a computer system to provide reliability and performance to data storage. Here, reliability is ensured by preventing data loss in case of disk failure by enabling easy and faster recovery of the same. In terms of data storage, performance is considered in form of ability to read and write data to a disk drive. RAID improves storage system performance by serving I/Os from multiple disks simultaneously. However, both data redundancy and performance are contradicting terms. We need to balance both based on requirement and sensitivity of data getting stored. RAID technology has now grown from theoretical concept to an industry standard and is a common implementation in today's storage arrays. Traditionally, we can implement RAID both using hardware and software methods. Let's analyze these methods one by one. Software implementation of RAID is done at operating system level and make use of host resources like CPU cycles, memories, etc. It doesn't require a dedicated hardware controller to manage the RAID array. Software RAID is also called as poor man's RAID solution due to its benefits in terms of cost and simple implementation. Administrator needs to play around software settings to manage RAID implementation without paying anything for dedicated hardware. Absence of hardware, on the other hand, also limits its implementation in terms of performance, features, and compatibility. Since RAID software consumes host CPU cycles, this may impact complete system performance. Moreover, in case of large data transfers or I/Os, performance of storage device is also impacted. Adding to whos, compatibility is another concern with software RAIDs. Since it is an application, it needs to have compatibility with underlying operating system, especially with every patch or upgrades. Hardware RAID uses a specialized hardware controller either on host or on the array. In host-based implementation, controller card is installed on host or on motherboard itself. Disk drive are connected with these controllers. On the other hand, in external array-based implementation, external RAID controller act as interface between host and disks. So, here RAID controller presents storage volume to the host and host manages these volumes as physical drives. A RAID array is an enclosure containing number of disk drives and RAID controller as a supporting hardware. Here, some disks are grouped together to form a logical associations called as logical array or RAID sets or RAID groups. Controller in RAID array provides three main functions. First is management and control of disk aggregation. As RAID controller is an interface connecting host and disk, and physical disks are grouped logical manner in an array, it provides translation of I/O requests between logical disk and physical disks. And lastly, it helps in data regeneration if disk fail based on RAID configuration. Now, how data is regenerated or restored in case of RAID? We will see that in upcoming sections. Now, let's analyze some of the concepts related with RAID techniques which showcase how RAID allow data storage in disk at logical drive. Stripping, mirroring, and parity are few of the common methods. All of them differ with each other in terms of data storage method to provide data performance and redundancy. We will discuss each of them in details to lay down foundation of RAID levels. Stripping is a technique to distribute data across multiple drives and use them in parallel. So during write operation, each disk in an array is broken into units or blocks and data is distributed into these blocks simultaneously. Let a host wants to write a string, data storage network and security. On receiving request, RAID controller distribute each word across drives in array. Similarly, for read operation, each disk contributes in retrieve of data simultaneously and send to controller. We should note that this example is just for sake of understanding stripping concept. We will further look into this concept with granular details. So as we have seen in stripping, read-write heads can work simultaneously. This allows faster processing of data and therefore increase in performance with respect to scenarios where read and write operations are done from a single disk. Now let's have some in-depth detail of how stripping works. Consider a scenario with array of 6 disks. When a write I/O request comes to a logical volumes, RAID controller helps to distribute all data to physical disk. Here, each disk is divided in small blocks, such as block 1 is on disk 1, block 2 is on disk 2, block 3 is on disk 3, and so on. Here, as block sequence forms a series of strips across the disk, hence this arrangement is referred as stripping. Data is distributed in a strip at a time, means each bit of data is stored in a block of strip, next bit got to another block on same strip and so on. Once all blocks are filled in a strip, filling of another strip starts. Disk in strip mode provides high performance or high speed as logical drive exposed to controller adds up to the speed of all physical drives under it. Say, if a logical drive or array contains 6 disks that are capable of handling 100 I/O per second, then capability of logical drive will be 600 I/O per second. Since all disks in a volume are getting utilized, disk using stripping methods offer zero capacity loss or overhead. However, stripping techniques provide zero fault tolerance due to absence of redundancy in method. So, stripping alone does not provide any data protection, but when combined with other methods, this drawback can be overcome. In upcoming sections, we will see how stripping method can be utilized along with other methods to provide RAID configurations. Strip size or strip depth or a chunk is number of blocks in a strip. It also shows maximum amount of data that can be written to or read from a single block. Stripe is formed from a row of chunks presented from all physical size. Mathematically, stripe size is multiplication of chunk size and number of disks in RAID set. For example, if we have a RAID set of 6 disks with each chunk of 16 KB, then strip size will be 96 KB. Strip width is number of drives in a RAID set. Since stripping allows data to be stored in parallel to all disks in a logical array, chunk size should be adjusted based on I/O size. In case I/O size is large, we should use smaller chunk to distribute data faster. On the other hand, if I/O size is small, chunk size can be increased. So thumb rule is larger the I/O size, smaller the chunk. Smaller the I/O size, larger the chunk. Mirroring technique makes same data to be stored on 2 different disk drives. So copy of data is maintained to ensure redundancy in case of data loss. Here, 2 physical drives are placed in a mirror pair so that data getting stored will be replicated or copied to another in parallel. In mirroring, logical disks have 2 mirror pair of physical disks providing medium to high performance irrespective of size of I/Os. For write operation, data is written on 2 drives, hence write performance is impacted by this. It can be optimized based on methods used to mirror data. One can choose to write data in parallel to both disks or can write to one and let it replicate to another in parallel or after some interval. During RAID operation, performance is good as requests can be serviced from both disks. Now, since equal amount of duplicate data present in logical volume, capacity of logical drive is decreased by 50%. For example, if an array contains two physical drives of capacity 1 TB each, capacity of logical drive exposed to controller will be 1 TB only. In case of fault tolerance, mirroring method can withstand a failure of one drive. So if we replace failed drive with a fresh one, mirrored pair of failed drive can be replicated its data and fault tolerance will be restored. Parity is a redundancy method that ensures data protection by checking errors, ensuring data integrity, and recovering data in a binary system. Calculation of parity bit is done by RAID controller. These parity bit can be stored either on an independent drive that is placed separately with existing disk drive or on one of existing drive that can be dedicated for parity storage. We can even distribute parity bit across all drive in a RAID set. Parity can be either even or odd, and it depends on user implementation and usage. Both types provide same results. In this lecture, we will use even parity in our examples. Even parity is implemented to ensure that there is an even number of ones in a row of data. Consider a RAID set of 5 disks. Here, last disk is dedicated to store parity bit. In 5-disk RAID set, 4 disks are used to store data and 1 disk for parity. In this scenario, incoming data is divided in sets of 4-bit each. Each of 4-bit is stored in a block of each disk, and parity is calculated to ensure even number of ones are present in each block strip. If bits in a data set are all 0, parity bit will be 0. If data set contain odd number of ones, parity bit will be 1 to make it even, and at last, if a data set contain even number of bits, parity bit will be again 0. Now, in case of disk failure or data loss, we can always calculate lost data in a disk using parity bit. Here, parity bit can provide measure to know which data bit is lost. Single parity is used to recover data from single drive failure. Similarly, we can use double parity to recover data from 2 drives. Overall, unlike mirroring, where we have capacity loss of 50%, using parity we have small capacity loss to store parity data, but in return, we have effective data redundancy. Now, let's look into arrangements and method used by disk drive to store data. These different configurations are also known as RAID levels. Stripping, mirroring, and parity techniques are used either independently or in combination with different RAID levels. Depending upon requirement in terms of data redundancy, performance, and cost, one can choose RAID level. Starting on different RAID levels, first in queue is RAID level 0 or RAID 0. RAID level 0 uses data stripping method where data is stripped across all the disks with a RAID set. Minimum of 2 drives are required to distribute data in strips. To read data, all strips are put back together by the controller. So as number of drives in RAID set increases, performance improves accordingly. RAID 0 is a good option for applications that need high I/O throughout, as more data can be read and write simultaneously. Like in case of video streaming, video editors working with very large files can use RAID 0 while editing multiple streams of video for optimal playback and performance. However, technically speaking, RAID 0 is not a RAID in itself, and it does not provide any data redundancy and high availability. So in case of data failure, data can't be recovered or restored back. Due to lack of any data protection, RAID 0 is not used as a single storage backup solution on critical systems. So we have seen RAID 0 is actually not a RAID configuration due to absence of any redundancy provided by it. Another RAID configuration is RAID level 1 or RAID 1. It uses data mirroring technique to provide data redundancy and high availability. In RAID 1, every disk is arranged with its mirrored set and data is written on both the disk. This provides low write speed. However, this performance impact can be improved by writing data on one disk and replicating to another in parallel. This improves write speed to some extent, as now instead of 2 disks, data is written on 1. But replication to another disk may not be real-time and consumes host CPU. On the other hand, as 2 disks are available in parallel for read heads to extract data, read speed is quite good. Data mirroring in RAID 1 is transparent to the host. So during disk failure, RAID controller has readily available disk to continue its operation and zero data loss is encountered. Once malformed disk is replaced, data is replicated to ensure smooth operations. It is best suited for applications which require high availability and performance. Apart from low write speed, cost is another constraint in RAID 1 implementation. Here, data is mirrored, so minimum of 2 drives are required to implement this technique, and out of which only one is used for actual data storage. RAID 1 suffers from capacity loss of 50%.